In my first year studying architecture, I built a land gauge out of sticks, vines, and a feather. I used this to create a visual device for observing the wind that I felt caressing through my skin and blowing through my hair. The specific site is characteristic of gusty wind and wild bird life. The feather I observed appeared to dance around in harmony with the wind. The shaft of the feather reminded me of the baton used by a conductor to create a visual device for an orchestra to view the timing and dynamic variations of a musical piece. Through my study of architecture, I've developed a philosophy based on an organic development that grows from the site. Architecture is an organic progression, growing from the surroundings, up from its place in the earth, through our senses, and into our minds. Through my journey studying architecture, I've learned that I must master many tools, beginning with anything that makes a mark on paper to computer-aided drafting and three-dimensional modeling. We can use spreadsheets, calculators, and even things we've not used yet. For MAA505 architectural thesis project, I would like to propose the use of a new tool to help analyze building designs for ventilation and thermal comfort. I pose the question, how can the use of new computational fluid dynamics simulation software help architects in the design process to improve natural ventilation and thermal comfort for housing design? Does this software add better value for predictive modeling in the challenges posed by hot, humid, tropical climatic conditions? To answer this question, I've selected 10 precedent houses built in North Australia's tropical hot wet monsoonal zone. I've conducted a review of recent research to understand passive design techniques and investigate new innovations in this field, particularly dealing with hot, humid, tropical climatic conditions. I've also reviewed historical research into houses in North Australia. A climate analysis was conducted for the locations of the 10 precedents, and the relationship between solar radiation, temperature, and relative humidity was observed. Then a protocol was developed for running these simulations using some of the climate data to observe the wind acting upon the 10 precedent houses. The 10 precedent houses, in chronological order, starting with a generic 2-room cottage determined from the research. Warringah House, a heritage-listed house currently located on the original site in Townsville when it was built in 1912. Paspaley House, designed by architect Harry Seidler and built in 1957 in Darwin. Draper House and the following Caplinger House, designed by Tropo architects Adrian Welk and Phil Harris in 1982 and 1983, both built in Darwin. Marika Alderton House, designed by Glenn Murcutt and built across 1990 to 1994 in East Arnhem Land. Kembarley House was designed by Tippett Schrock Architects and built in 2009 on Magnetic Island in Townsville. Connell House, designed by Tropo architect Aftab Kamisa and built in 2011 on Magnetic Island in Townsville. Inside Out House, designed by Ruth Brown and built in 2014 in Darwin. And finally, Gavin House, designed by Pod Architects and built in 2019 in Cairns. Prior to performing the analysis, a review of historical research was conducted in the aim of understanding how the form of tropical housing in Northern Australia evolved over the years. The most significant aspect observed at floor plan is how the plan opens out. In some cases, it creates a cluster of pavilions connected by covered walkways. By doing this, breezeways replace hallways, and the outer wall space is significantly increased for each room. More opportunity for openings to ventilate internal space results. The large openings and roof overhangs are typical of a tropical house. The veranda of a tropical house works well to regulate the intense velocity of wind before it enters the house. Warringah House and Kaplinger House demonstrate this in the analysis. In most cases, the house appears to repel heavy, gusty winds, but allows for steady, low-intensity breezes to enter the house and continue to the other side. Paspaly House is the best example of this. Looking at this particular house in an east or west elevation, one can relate the form to a section of an aeroplane's wing, as seen here. When analysing ventilation, it is crucial to understand the physics of airflow. In fluid dynamics, liquid and air are both considered fluids, and solid mass is excluded from this category. The reason for this is that any movements of particles within solids remain uniform, and particles within liquids and air move more independently of each other. As fluids begin to flow, the energy causing the movement is potential energy, which carries the momentum of the fluid at velocity, and the mass of the fluid tries to remain uniform in flow direction. This is called laminar flow, and this word can be thought of as being similar to laminated sheets which are parallel to each other. When the fluid encounters another mass, whether it be a solid or another fluid, friction occurs at the colliding surfaces. The friction occurs at different intensities caused by the viscosity of each mass. The friction can cause portions of the mass to change direction while it continues the momentum driven by the potential energy it began with. Thinking of the fluid as it changes its directions and moves away from the laminar flows, this is the transitional phase. The air mass continues in its general course. As it builds friction with the other mass, it begins to roll and create eddies. The potential energy converts into kinetic energy, which is a transition from the stored energy in the velocity to the movement of the particles within this chaotic flow. As these eddies roll and mix with other fluids, they begin to deform and dissipate the energy into the surroundings. This is called turbulent flow. Laminar flows are more favorable for ventilation as they will enter a room, pass by the occupants, collecting heat as it goes, and then exit the other side of the building, taking the heat with it. This occurs at lower Reynolds resistance or a low Reynolds number. As the Reynolds resistance builds, the transition phase occurs and then air flows become turbulent. Turbulent air flows will tend to linger and deposit energy it has collected into the area where it dissipates. This means the heat energy it may have collected remains and any built-up heat will be added to it. The Navier-Stokes equation is a partial differential equation to describe the motion of the fluid and the friction of the air in chaotic turbulent flows. This is a very difficult equation to solve as it can account for a massive amount of eddies within turbulent flow. So CFD software compensates for this by using the Reynolds resistance to average out the eddies that the Navier-Stokes equation predicts. This is referred to as the Reynolds averaged Navier-Stokes or RANS model. With this fundamental appreciation for physical airflow, we can build a vocabulary for analysing wind and ventilation acting on a house. We can turn our perception of a dance that the wind does through and around a building into a comprehension of the choreography that the house commands of the wind. Current climate design strategies have been developed in more temperate climates. However, in tropical climates, analysis specific to the site conditions is required for better design strategies. This tool, CFD simulation software, increases the resolution of the architect's analysis to better predict ventilation in buildings, just as architecture is an organic progression growing from the surroundings up from its place in the earth through our senses and into our minds. The way these visualizations add the inhabitants and furnishings of the house into the analysis can help the architect to understand and communicate how natural ventilation can enhance the lifestyle, particularly in tropical housing. From this quantitative-based analysis, we as designers can enhance the design with the qualitative visual representations of these beautiful images. Taking this research further, CFD software can be used for optimization of designs in the process of generative design, and the imminent arrival of artificial intelligence in the design process, I propose that architects will be able to lead the way in designing the design process. Thank you.